Alright, so let us continue with talking about some harmonic motion and the idea of restoring forces. So, let's say for example, we have spring, something like this. We have some mass attached to it like that. Okay, and it's attached to the smooth floor, something like that. It's on the smooth floor like this. Okay, something like this. Now, consider this the natural position of this mass like this. It's on the track. This is at x equals 0. We'll call it equilibrium, or the origin point. Okay. Right, recall these situations from Hooke's law, which we studied earlier in the book. And we're coming back to it again. So let's say I have it compressed, right? Let's say I've compressed it like that. And we'll call this position A. Okay. We'll call this position, and this is some distance from the origin point. That'll be called A or minus A, something like this. Okay. Like this is a situation where we compress the spring. This is its equilibrium. This is the compression of the spring. And this is, of course, last situation here. And this is like the maximum stretching of the spring like this. And this is stretch like this. And this is the plus A like this. And we call that plus A the amplitude. We call that A the amplitude, which is simply the maximum displacement, the how far I can go. And I'll write that in the next page for us. Okay. Is the maximum displacement or minimum from equilibrium. Okay. And we use the symbol capital A for that. Or sometimes lowercase a you'll see in the textbook as well, but they don't want you to confuse it with acceleration, so we'll use capital A for it. Okay. Right, and we measured amplitude, of course, in meters, or whatever unit of length that it will be. Sometimes centimeters, sometimes mostly for meters. Okay. Okay. And remember, it's from equilibrium to maximum, and we'll graph it all eventually and see what we mean by that. Okay. And so when we graph it, it looks like this. Right? If we graph a sine wave, for example, our amplitude is the maximum and minimum values here. Right? It's how far from equilibrium, which is here. This point on the axis right here, this is equilibrium. This is equilibrium on this point. Okay? So it's very important that you keep that in mind. It is not the full length of this wave. It is only from the point of equilibrium. Okay? Make sure you keep that straight. Right? We talk about full length of the wave later. That's called wavelengths, but we'll talk about that later. Right. Now, when our restoring force is linear or following Hooke's law, it's simple harmonic motion always. Okay? When we're following Hooke's law, which is what we have given here, that's when we're going to be following the simple harmonic motion rules, which we'll be talking about here. Okay. And ultimately, it doesn't matter whether the spring is horizontal or vertical. It's exactly the same principles involved. Okay? The principles are exactly the same involved. Like if I draw a vertical spring, for example, clear it. Right. This is my equilibrium position. Okay. Like the spring without mass attached to it in the vertical situation is just the equilibrium position. And then when I attach the mass to this system, I stretch it out. Something like that. This is my x equals 0. And we have our uncertain string. And so equilibrium in this situation here is not quite at x equals 0. So at this point here, we have the spring force, which points up, right? If we draw the free body diagram here. At this point, we have the force of the spring with up, force of the weight going down. Okay. Something like that. Okay, this is our equilibrium position here. So here, I will draw it out. This is equilibrium position. Why? Because the sum of forces in the situation is 0. Okay. So, if this is 0, right, I already can tell you that force of the spring minus the weight is absolutely nothing. Okay. And if I solve this equation, of course, for the distance that this makes here from this point, called delta y, so we have force spring equals mg, which is weight of the object, and so we have ky equals mg, and so y is equal to mg divided by k. So we're just using y because it's on the vertical axis in this situation. And if I push, And if I push up in this situation, or if I pull down, doesn't matter. It doesn't matter really at this point. Okay. But what gravity allows us to do in this situation, the force of attraction, allows us to find where the point of equilibrium is. Let's write it down. It's very important for you to remember. Okay, I'm going to erase all these images here. So, right, gravity in a vertical spring helps us to find the point of equilibrium. Helps us to find the point of equilibrium. And because all it helps us to do is to find the point of equilibrium, we don't need it necessarily to find out how to get the restoring force in that situation, how to restore it. All we need gravity to do is help us to find where equilibrium is, right? And then we realize that to get back to equilibrium is dependent only on its position and not gravity at all. Okay? So that's one kind of example. One kind of example of simple harmonic motion, where we have a repetitive motion that follows a sine or cosine curve. Okay, and we'll go into more into math later. Another example of this is the pendulum problem, which we have done a little bit of earlier, but we'll focus it more on this chapter. Okay. Well, so here we go. Let's erase it. So we have our pendulum, something like a clock, right, of the pendulum. Okay. And the pendulum, there's the bob on it, like this is the angle theta, right? And this is, of course, length of the arc that it travels along. And will travel to exactly the same point, we're assuming no air resistance. I can't really draw, but I'll have to do. Okay. So in this situation here, right, well, this is a situation like this. But if we draw a free body diagram, looks like this. Tension at the angle theta. We have tension at angle. Okay. And then here we have weight like this. And if we break it, we have weight here. We have tension of the rope or the string like that. Okay. It can be rigid or non-rigid. And of course, if we break it, and this is the angle theta, we know from Newton's law, sum of forces in x direction will equal mg cosine of theta. Oops, sorry, not mg sine. Sorry, wrong angle. Mg sine of angle theta right? And you know sum of forces for the y direction will equal tension minus mg cosine of theta 0. Okay. We're assuming no air resistance. We're assuming no air resistance or something like that. No friction for us to work with. Okay. And so it's the component of weight which will bring the tension, which will bring this pendulum from its starting position. Like if I hold it back at some angle and let it go, it's the weight of the pendulum, right? Kind of like a swing. Like when you guys go play on swings on the playground, like when you guys were kids. This whole idea of the pendulum is what's going on. So like you swing yourself back, you start up high at an angle, and you let the weight of the motion carry you. Okay, same idea here. In this situation, this is what's restoring us back to the point of equilibrium. Alright, and the point of equilibrium is of course in the middle when the tension of the rope and weight are exactly the same. Okay. Alright, so it's very important for us. Okay. And your textbook talks about what happens. This calculation isn't really hard. If we make the angle small, if we make it from 0 to 10 degrees, ironically the same definition for theta to be vector in radians, but we're using the sine of theta is approximately theta in radians, and of course we can prove this limit from calculus, but I don't want to, so we're not going to. Okay. Let me clear this out for you. Okay, so if we restrict less than pi over yeah, yeah. So okay, I'm right. So pi over 18. If the limit is less than pi divided by 18, it's about 10 degrees. Okay, we can say sine of angle theta is approximately theta. Right, this is only true for theta in radians, not degrees at all. So make sure that you have it in radians. Okay, when we're doing the calculations. So our angles here, we have to keep the angle, of course, in radians, not degrees. Okay. So when we limit the angle to something small, our pendulum follows simple harmonic motion. The idea it has a sine and cosine curve. If we limit the angle. If we do not limit the angle, then we have different situations, and we'll talk about that later in a different chapter. Okay. And remember, remember what happens with the restoring force. That the farther away you are from equilibrium, the larger the force is, because you need more force to bring it back to equilibrium. Okay? So this would end that. And we'll talk more in detail about it later. Right. In your textbook, you have this stop the question, we'll answer it right away here. Alright. So, if we have a ball that's hung from rope making a pendulum, When it's pulled to 5 degrees side, the restoring force is 1 Newton. What will the magnitude of the restoring force be when it's pulled to 10 degrees side? Okay. Okay, so it's the question from the book. What is your guess? Harasho, very good. 2 Newton is very good. It's the correct answer amongst the choices. Letter D is the correct one. As I told you, that recall that only is proportional to displacement, in this case the angle, is functioning as your displacement. Since the angle was doubled, the displacement has to be doubled. Or in other words, the farther away you are from equilibrium, the larger the force needs to be to get you back to equilibrium. Okay? This is what we talked about. Now, next section we'll talk about the mathematics in describing harmonic motion.